Dear participants and professors, after the lunch break, now the next part of the International Second Technology in Medicine Symposium starts. We are very grateful for hosting our valuable professors and participants as Neuroscience community. New attendance for the English part of the symposium, welcome to all. I am Sude Gücük from Ankara University, Faculty of Medicine. We would like to remind you that with the start of our professor's presentation, 6 session attendance form will be open for answers, and with the end of the presentation, the form will be closed. Then we will move on to the question and answer part. You can ask your questions by filling out the form that we have shared with you. Please note that since we will prioritize English questions, we kindly request you to ask your questions in English. Our next topic will be Wearable Bioelectronics in Medicine, with the presentation of Assistant Professor Onur Parlak from Karolinska Institute, Bioelectronics Department. He made us very glad by accepting to be a speaker at our symposium. We thank him again. Now, with your permission, I am going to turn off my camera and leave the floor to Dr. Parlak.
All right. Thank you so much, Sude. Thanks for the invitation for the whole Neuroscience Society and all students organizing this very good seminar on Sunday afternoon. So you already introduced me, but very briefly, I can say a couple words. My name is Onur Parlak, an assistant professor at Karolinska Institute and Department of Medicine and Dermatology and Venerology unit. And also I'm partially affiliated with Ames Center at the Neuroscience department. So today I'm going to talk about the wearable bioelectronic in medicine and how can we use this new technology for the healthcare applications. So before start, I would like to give very brief introduction about myself. So I am chemist, both Bachelor of Science and Master of Science in Chemistry in Izmir Institute of Technology, Department of Chemistry. And then I moved to Sweden and Linköping University in 2012, and I got my PhD degree on bioelectronic in 2015. And then with the support of Wallenberg Foundation as a private in Sweden, I moved to Stanford University for postdoctoral research at Material Science and Engineering Department. Following that, I came back to Sweden and Karolinska Institute Neuroscience Department. I worked about 2 years as a research fellow at Neuroscience Department. And then recently I was awarded by Karolinska Institute Strategic Foundation for the Future Research Leader and the Group Leader. And I started my own group, Department of Medicine, in June 2021, still continue there. So today, what I'm going to talk to you about is a short introduction about the human skin and how we use the information we obtain from human skin and how we combine these things with technology. And I will discuss very briefly about wearable technology and why it's important. And at the end of my talk, I will summarize a couple work that I have done. I completed recently back at Stanford University and now here at Karolinska Institute. So it will be about continuous monitoring of hormones and ions through human skin. So before start, I would like to introduce very briefly about the human skin, which is I really enjoy talking about. The skin, fun fact, I call the skin is one of the biggest organs that we have. It covers approximately 2 meters squares of the area. And then most importantly is account about 15% of our body weight. And it's very good things that it's very interesting, the features of the skin that it renews itself, constantly shed cells, dead cells, approximately 30,000 cells for every minute, which makes approximately 4 kilograms per year. And also home more than 1,000 species and different microorganisms, not 1,000 species, different type of species exist on human skin. For those things, we are interested in skin because changes on human skin can signal changes over health. So for those, we call actually skin is the ultimate sensor. The sensor that sense around us, sense everything what's happening in our body, and then reflect to us to see it visually. And of course, we integrate some devices to understand better those phenomena. Skin is not only the ultimate sensor, it is also first line of defense against environmental factors like bacterial and virus invasion or environmental pollution or UV light and such. Beside that, also skin act contains so many the sensory receptor to interact with the environment that recently, as we know, the Nobel Prize goes to this sensory receptor can understand cold and pain. So those receptors locate just under the dermis and help us to communicate this information, outside information, with the central nervous system. And also I call the skin as a temperature regulation and a little bit point of chemist point of view, I call it also chemical factory. So many reaction happening and so many new the product, the materials, chemicals produced in our skin. Beside that, skin is also very interestingly that we don't see any other organs that we use as a tool for self-expression for over 10,000, 20,000 years since the human exists, better to say. So we make a tattoo, we make it different shapes and everything just to express how we feel, how we communicate with each other. For this respect, the skin is a very important organ. But skin is not skin is fallible. It can sometimes fail. And when it fails, some different diseases start, like as you see here, dermatitis, skin cancer, acne, psoriasis, and such. Of course, not only that, there are some genetic background that disease is happening, but when it's happened, then we are very prone to many disabilities even sometimes. And costs so much to economy as well, is about $75 billion only in 2012 and only in United States skin diseases cost. This value is approximately similar in European Union, and we don't know so much detail, but even I expecting much higher values can happen in the underdeveloped country or third world country as well. For those diseases and many others as well, we are trying to integrate wearable technology to solve this problem, or at least the sense before, diagnose before it's happened. So in our lab, we mainly, our core interest is developing skin sensor for the healthcare application. But when we look at the literature and we just Google many different applications of wearables, that you may see a lot of other things, such as, for example, people use the lactate monitoring for to understand the sport performance, or they integrate these wearable devices, the smart gadget they call it, just to interface with the mobile devices. No healthcare emphasis, no other applications other than just reflecting the things on our skin. Beside that, there is also different approach, a little bit the science fiction type approaches, but it will definitely come in the next couple decades, like going beyond the physical, chemical, and biological parameters and developing electronic skin to replace the skin maybe. We are not there yet, but of course, there are very interesting research going on all around the world. So as I said, we are interested in developing wearable devices, mainly sensor, to continuously monitoring the human machine. So how we do that, we are integrating different the sensor devices with the contact lenses. We make sometimes the implantable, integrate this sensor in wristband, clothing, and shoes to continuously monitor, as I said, the human parameters. But why we do that? Who cares? Why is it important? Which is the important question that we have to ask before start any kind of study. One of the main reasons that we do is wearable devices that we imagine can provide rapid and personalized diagnostics and to tackle the limitation of centralized reactive healthcare system. And this enables individuals to monitor themselves without expensive equipment or the trained professional without going to hospital and such. So these are very general the motivation of our work. And also it started to emerge this market also emerging for the wearable diagnostic devices. Most of the current, actually, the market value is about $75 billion. But all these devices, majority of these devices like wearable cameras, electronic textiles, and skin patches. And the share of medical diagnostic is less than $1 billion and mainly dominated by blood glucose sensor. And there are so many different opportunity and kind of so many other things can be done, better to say, for those, but it's really started to emerge very recently. So we are one of the groups working on those things and integrating wearable for the medical purposes. So how we do that? We do different design. This design can be, as I said, integrated with many different things, like for saliva, to monitor, for example, the oral health, or tear-based sensor. We can integrate the lenses with the electronic devices, but mainly our focus is a sweat and interstitial fluid-based sensor to monitor the health parameters. So what we do for this, we initially started our project designing wearable bioelectronic in sport medicine, and we were wondering how hormones, metabolite, and ion level change during intensive sport activity. For those, we need to look first what we have, what kind of information we can access. When we look at, again, there's the chemist perspective, I realized that when I do the literature search and everything, we can access more than 800 chemicals. When I talk about the chemicals, all these things are electrolyte, amino acids, proteins, metabolite, and hormones. In our lab, as you see here, there's all the red colored things that we are focusing on right now in our lab. Some of them we publish, some of them we are still working on. One of the things I forgot to mention, that the core topic that I will talk to you today is kind of designing cortisol sensor and ammonium and calcium sensor. Because monitoring the stress, monitoring the cortisol is very important, and there are different technology already exists. But before knowing designing the wearable devices for stress monitoring, we have to know what's happening in our body. So one of the first thing happened that we start to sweat. And the second thing, our body temperature increased and our frequency of movement increased more than usual, because we worry and such. So there are devices that I'm wearing today. One of those as actually say some values. For example, when I prepare one of my presentation, I took this picture to understand how stressful I am. Luckily, I was not so much, but you can get some information, but those information actually all physical parameter based on temperature, the perspiration rate, and the movement frequency. So all these things calculated by the software and algorithm, and this algorithm give you some value, like as you see here, 30. But what is 30? There is no meaning in terms of medical diagnostic. So in order to make the medical diagnostic, we need to go beyond these physical parameters and follow the chemical footprint of the stress. There are two molecules that we know is very commonly known as adrenaline and the cortisol. In our lab, we are focusing on the cortisol because adrenaline is, even though it's very important, but it fluctuates during the day up and down. So that's why the cortisol relatively more reliable, because once it increases in the morning when we wake up and decrease gradually until we sleep. And if some stressful situation happen, then we can easily understand we're really stressful or not. So that's why we are following the cortisol. And the cortisol, not only for, of course, the sport medicine, it's related to so many other things in our body. Like, as I said, when we have stressful condition, our skin start to have some problems. So we develop gradually skin inflammatory disorders. And the same things valid for immune system, reproductive system, and heart and headache and such. So when stress happens, first thing is that inflammation occurs. When this inflammation continue, then disease start. All these diseases, cardiovascular diseases, metabolic diseases, mental diseases, which is very important. And of course, and many other skin diseases as well develop just because high level of cortisol. And this is, the neuroscientist is very well aware, this system, this is HPA axis. For example, when we are in the stressful situation, and the first what's happening, there are a chain of the hormone reaction happening in starting hypothalamus, pituitary gland, and overall adrenal gland, the secrete the cortisol molecules. And all these the molecules diffuse very different part of our body: saliva, sweat, interstitial fluid, tear, urine, and even hair. We can detect the cortisol molecule by the help of this mechanism. So for those, we need to design the sensor. As I said, we are designing the sensor, but for those, we need to have the kind of a membrane that senses this cortisol in our body fluid. So this cortisol molecule should react or bind somewhere that we can understand how much cortisol we have or not. For those, we are using a very well-known technology, actually, the molecular selective membrane or molecular imprinted polymer, you can call it. So this basically the polymerization mechanism that you have a template molecule, the cortisol in this case, you polymerize, and then this is non-covalent assembly, kind of create 3D network, and then you move this cortisol molecule, and at the end you create kind of molecular memory introduced by the subsequent removal of imprinted molecules. With this way, we are taking these membrane molecules after following several of reaction. Actually, just the summary you see here, we have 30, 50 different the combinations that we follow, and we choose the best the conditions, and then apply all those membrane on the device. I'm not going to go in details today, the device side, but we're also designing the polymer-based, conductive polymer-based organic electrochemical transistor. This is kind of the two one-channel devices that we coat our the device with the P.PSS first, the conductive material, and the second layer, we make the cortisol imprinted polymer, this molecular membrane that I've showed you previous slide, is the second layer. So what's happened here when we sweat or any body fluid interact with this membrane, all molecule pass through, but the cortisol binding there and increase the kind of surface interfacial conductance, the resistance, and all the molecules pass through, and the transconductance of the device change over time. So this is how it works. We also control this measurement that we do with non-imprinted polymer as well. So here you see one of the devices that we had done, for example, testing everything before applying to skin. We designed very small, the kind of credit card sized device that we call skin-like microfluidic channel. And this is two PMMA molecules, polymethyl methacrylate, laminated together. And then we are using the laser, the CO2 laser, non-invasive laser, and we create small pores on it. So this pores looks like the skin pores, the sweat pores that we have. And then we injecting the samples there, that sometimes real samples, sometimes it's artificial sweat. We're injecting from one side, and all this molecule diffuse through this skin-like microfluidic. And at the end, we have this flexible, the wearable molecules, not wearable in this case, at the end of channel. And then we are sensing the cortisol, increasing cortisol and decreasing cortisol concentration. We are obtaining our calibration curve. And then when we inject the real sample, the value that we read go to the calibration curve, then we understand how much cortisol we have in real sample. So after making sure that our device is working with skin-like microfluidic, we apply those things to the wearable device in real human sample. For those, we have very small patch that we illustrate here that I'm going to show the real picture now. Is a 4-layer device. In this 4-layer device, we have first 2 layers. We call it sample acquisition layer. The first is sample reservoir, and the second was microcapillary channels. This microcapillary channels is the channels that interacting with our skin, as you see here. It may look complicated, but actually it's very simple 3M medical tapes. So we take this medical tapes, and again, we go to the laser, we create very small pores. The pores looks like really like our the sweat pores that you see here, that the picture that I found on the internet. And we create this type of pore, and it create kind of capillary action without powering the devices. When we sweat, all the molecules all the way goes to sample reservoir. And then the third layer that we have, the molecular selective membrane. This molecular selective membrane also contains several layers. The first, flexible substrate that we have source, drain, and gate contact. This is kind of electronic device. And we coat with first PEDOT PSS, conducting polymer. And then the third layer is the molecular selective membrane. And then we cover everything with the waterproof protection layer. So here, when we look at the molecular selective membrane, that you see the membrane on the here AFM analysis, and then we have the control device as well. So when you look at the SEM, you can see maybe more detail that all are small molecular beads. But when you focus these things, you can clearly see the difference. For example, this is highly porous material that we create because the cortisol molecule binding there and then moving from the membrane and left, as you see here, very porous things. And here is the control that we don't start the reaction with the cortisol, just the polymerization. And when you go this one, you will not be able to see the porous structure. And you can see the same things with the BET analysis. This is the analysis of the porosity analysis, how much surface area of the pores, the pore diameters and such. And as you see here, we have 10 times more the pore surface area compared to control material. So what we do then, this is the real device, how it looks like. Very simple paper-based devices that we have all the contacts here. And we put the sensor on our skin and we go to the campus in California, 30 degrees, 35 degrees sometimes. And we run about 30 minutes and came back to the lab. Without taking these devices out of our skin, we make the connection with the cable. So this is very preliminary device that we have now. We are trying to improve these devices and making fully integrated. Everything will be integrated on the simple device that we don't need to even come to the lab and measure. And we will just take our phone, and while we are running, we will be able to measure the cortisol concentration. So this is a real sample analysis that we have done. And this is, as I said, how things go. This is how we started and now how we are moving at this project further, integrating with different electronic components in order to make it a fully integrated device. So when we look at this field a little bit, the historical timeline, and back in 2018, we were the very first group designed this wearable cortisol sensor. There were cortisol sensors available in the literature, but we were the first group developed this wearable cortisol sensor. And after that, several groups followed sometimes the same strategy, sometimes a little bit different strategy. For example, the Vega from the Caltech, it designed very well, fully integrated device, 2 years after us, by integrated antibody-based sensors instead of using molecular selective membrane. And another group that I know also integrate these things, go a little bit further and integrate with this very tiny small electronic with the contact lens and measure the cortisol level in human tear. All this work still continue. There are many papers coming out, and it's really interesting to see how it will develop over the years. So as I said, we did this study for the sport medicine. It was my real intention at the beginning, but we got so many different interests all over the world. And I started also collaborating for those things for more neuroscience, like mental health and epilepsy monitoring. And also it was interesting to one day receive email that people want to detect those, integrate 1-hour device for the livestock monitoring in order to understand, for example, the efficiency of the livestock and then production and the chain. And also right now I'm working dermatology department and the dermatology unit in the Department of Medicine. So we are also interested to see how this stress level affect the skin health and dermatological applications. So all these works evolve over the 2-3 years in different direction. So I always like to suggest this book to everyone. Professor Robert Sapolsky, in the Stanford University professor, that he actually talking about the stress, how it's affect the other organ, how it's related with the other disease and how to cope with. And you can also find many different the talks in YouTube available. If you are interested in, I strongly recommend one of the best, the non-scientific book, the popular science book that I read. So I strongly recommend everyone. So another things that we are doing. So there was a couple of other questions that we want to ask. For example, is it possible to perform the multiplexing? Instead of measuring the one molecules, can we do two at the same time? The other question was, is it possible to do long-term measurements? So for those, to answer those, yes, we did both of them. The first of all, we keep the same device concept, but instead of one channel, we do the two channel devices. And again, we have the flexible material and PSS conductive polymer, and we targeted ammonium and calcium ion at the same time. But to sense that, we are, instead of using molecularly selective membrane, we were using already commercially available technique, the ion selective membrane technique, by using ammonium selectophore and calcium selectophore integrated in the polymeric structure. This is basically how it works. We just use here, this is not what material looks like, but we like this the distribution, the description, that like the membrane that we have like a filter paper. Then you wet this filter paper, all the molecule that you want pass through the channel, creating kind of a nano channel, the membrane, and other ions cannot pass. Once this ion that we want pass, and the PSS molecule interact with this ion and then create the electrochemical signal. So this is how it works in general. We also, as I said, did the multiplex sensing. We did two measurements at the same time. It is very similar size devices, but smaller channels we did to keep this the size as small as possible. And then we did 2-3 subjects instead of one subject, and we measure over time. So how it changed. And this is how you see one of the volunteer result. For example, ammonium concentration increases gradually over time, the 1 hour, almost double. And the calcium level decrease over time. This is one of the first study that shows how the calcium level change in the human sweat during sport activity, which is very important combination with the molecules that we are right now working on for the renal health. For example, for sport person doing the running very long term, when the calcium level increase or decrease significantly, then it may end up in renal failure, and that you cannot, for example, if you run marathon and such, you have to monitor these important parameters, especially for sport person, is very important parameters. So now I'm in medical school at the Karolinska Institute. Our lab aim is to translate this wearable technology in medical settings. So we already start many different collaborative study. One of them, maybe the next time I will go into detail, developing the wearable sensor for epilepsy prevention and prediction. So we make similar devices to monitor the people cortisol level, and to kind of combine with the drug delivery application as well to prevent, and also before epilepsy, epileptic seizure comes, predict this event way before it happened. So which is very important. And also another interest in my lab is actually the wound healing, the monitoring certain bacteria in wound. And we also interested in designing small sensor for the preterm infant, because they have very different skin structure than us. The top layer is not really developed. That means we can really get so many information without kind of being invasive on the skin, which we are interested in. And also, as I said, the glucocorticoid, mainly cortisol, is very important in the inflammatory skin diseases, that we want to apply those things for the early diagnosis of this disease before happen. So before ending my talk, I would like to give some conclusion and take home messages. The one good message is that everyone in this symposium can agree that it's very useful for remote monitoring to reduce doctor-patient interaction using the wearable devices, and you can get very valuable information, and you can get really medical diagnostics. A little bit the concern about the wearable devices, that imagine that we are wearing a couple of devices, or one device is measuring so many different parameters. One concern that how we are going to store this data, and how we handle this data, and who will access to this data. This is one of the biggest concern in the field, and is not very well established. And another thing's a little bit dark side of the wearable devices. For example, one of the Popular Science article was talking about how mobile health, we can also include wearables, could actually make people sicker. Because very important things that what you want to detect and who you will see those results. For example, in the pilot study, people integrate these sensor devices on the babies, and the parents was following many parameters. And it is very actually dangerous because parents get paranoid and they don't know what's happening, what is the meaning of this result. So that means we really need to know what to measure and how to measure and who should evaluate the result. These are important things that we have to consider. So also, before ending my talk, I would like to give a couple of announcements. This is one of the first book that we did, Wearable Bioelectronics, together with my colleague. And we try to describe this field because it's an emerging field. And if you are interested in, you can find on internet, and it can be kind of nice study. If you are interested in this work, it can be kind of the reference work for you. And another thing, the special issue coming, I'm one of the co-editor of the Wearable Bioelectronic, Biosensor and Bioelectronic issue in Journal of Biosensor and Bioelectronic, which is available for submission until the end of this month. And together with other co-editors we do. And also, as I said, I'm still carrying out this, my ambition at the beginning, want to design this sensor, and I established my company now, and I'm co-founder and the CTO at the Bioelectronics AB, and that we do these things in order to sense the physiological parameters during the sport activity that we recently started. So before ending my talk and passing the torch to the next speaker, I would like to take my team. Some of them already graduated, the Parlak team at the Karolinska Institute, and of course, Alberto Saleo team at Stanford University. I was there as a postdoc several years ago, and of course, the foundation for the support of our research. So thank you so much, and I will be happy to answer your question.
We would like to thank Onur Parlak for his speech. Now we move on to the question and answer part of our session. Our first question, how did you shift from a master's in chemistry to PhD in bioelectronics? Sounds interesting.
Yeah, yes, this is actually the thing that I really like to talk about. So in my research of 10 years, 15 years career, I really like to go going out of my comfort zone. This is the word that I like to say, because I started as a chemist, but I was always interested in doing different things. Sensor was one of the things. And this sensor research bring me to meet with the electronic people and combine chemistry, sensor, and electronic. And at the end, now when I'm in medical school and applying those information that I collected over 10 years now for the medical purposes. It's an interesting story. You never know where to start, where to end up. My master thesis was about polymer chemistry, making transparent composite material. And now I'm in Karolinska Institute and doing mobile health devices. So it's interesting journey. Yeah.
Thank you. And our second question, would we use wearable technologies to monitor cortisol or other metabolites in the brain?
We are detecting those things, circulating cortisol, not directly on brain. This is a bit sensitive. We do cortisol, creatinine, glucose, lactate, and many different ions. But yes, our device can measure circulating cortisol level and detect when you are stressful, when you are running and such. But now we want to apply those things for people having, as I said, epileptic seizure and such. We don't know how it will work, but we want to detect those things in advance. Any other question?
And our last question. As we know, with the non-invasive electrodes, sensors generally record unwanted signals too. In this stage, how we can integrate with different devices such as smartphone? Is it about filters?
About what?
Filters.
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 Yeah. Yes. when we do the devices, we make it special, right? So we have the sensors, the biorecognition unit that detecting the molecules that we want to detect. So we are kind of blind to other molecules that we have. So that's why making special electrodes, specialized electrode is the critical things in biosensor design. Otherwise, of course, you will put the device, you will measure so many things and you don't know what is it. So that's why we make it, we are using the selective membrane, ion selective membrane in order to pick the molecules that we want, and we are blind to other molecules. We just detect what we want to detect. So it's not creating any, it's kind of itself as a filter, doesn't create any noise.
We would like to thank Mr. Parlak for all his contributions. Before concluding our session, we would like to present our professor a certificate of appreciation for his participation in our symposium.
Thank you so much. It's really great pleasure to be here. Thank you. Thank you so much.
And after our break, our symposium will continue at full speed with the presentation of Mr. Ajmal Zemar. Stay with Neuroscience.